the presentation will be about motion adaptation in the context of dynamical distance geometry. So yeah, there was a lot of overlap with the first speaker today, but we are looking mostly at the problem from a distance geometry point of view. Right, so I'll give you an overview of the presentation. I'll start by introducing the dynamical distance geometry problem. Then I will talk about 2D motion adaptation and how this relates to the dynamical distance geometry problem. Then I will continue to 3D motions, predominantly human motions. So these are motions with a skeletal structure. And then I will talk about the problem of human motion retargeting, which the first speaker also spoke of today. All right, so what is the dynamical DGP? Well, in previous talks last week, we've seen the definition of the regular distance geometry problem, but in our case, we have a temporal side to it as well. So in our graph, the vertex set consists of objects paired with a time and temporal instant. And then our edges in this graph represents whether or not we know a distance between two of these vertices. So two vertices could also be the same object at two different times. And then finally, we have a mapping D, which maps a priority to such a distance. The definition of the dynamical DGP in dimension K is that we're trying to find a realization in the same space K, such that the penalty function sigma is minimized. And I'll show an example penalty function that we used in our project, in which we use these priority levels for the distances. And we measure the difference between the ground truth distance and the distance we have in the realization X. And an important property of this penalty function is that it is differentiable when the distance and the priority levels are positive, which means that we can use certain optimization methods, such as gradient descent, to optimize this penalty function. So now let's talk about some 2D motions. So when I talk about motions in 2D, I will talk about simple shapes that move frame by frame. So here we have an example of two squares crossing from opposite sides of a box. This picture is an overlap of all 12 frames of this motion. So the earlier the time, the darker the color of the square. Yeah. So then I will talk about motion adaptation and how this relates to the dynamical distance geometry problem. So given such an animation like the one in the previous slide, we can create a dynamical DGP instance in which we want to preserve the motion. And we do this by including the distances between every vertex and itself in the previous 3 frames. And then we can add something extra, like we can try to avoid collisions by making sure that all distinct vertices, or distinct objects in our problem, keep a distance that's at least larger than a certain threshold delta, or that this delta is positive. And then we make sure to assign the priorities in such a way that all the newly introduced distances have a maximal priority, because distances between frames that are closer are more important. Now let's see some results with this previous 2D motion when we include this collision of avoidance constraint. This was solved, this instance, by using a non-monotone gradient descent method, which works well for finding local optima for non-convex methods, just ours, such as this problem. So in the picture, you see 3 times this animation. On the left, we see the original, and then on the right, you see 2 values for delta. And you see that the squares start to avoid each other in the middle of the animation, because this is when they get close, and then they try to avoid each other because of this distance constraint that we added. Okay, so now let's move on to the 3D motions, in particular human motions. So in these motions, we have a skeletal anatomy, like the one shown in the picture on the right, which can be represented by a graph where the vertices are the joints of the skeleton, and the edges are the bones connecting these joints. And in our project, these graphs were a tree, where the root node of the tree was the hip. And if you have such a graph, such a tree, then we can provide a posture, the first posture of the human motion, using the function on the slides. We can look at the embedding in the 3D space. So now let's talk about how we can then represent a human motion using these skeletal structures. A common way to represent such a motion, which also the first speaker today mentioned, is by having a list of angles for each joint. Specifically a triplet of angles for each joint, 3 Euler angles, commonly referred to as pitch, roll, and jaw. And then in original posture, which in our case was a T-pose, like in the bottom left, all of these angles are set to 0. Using these angles, we can, and using the tree, we can basically describe the orientation of a joint compared to the orientation and the displacement of a joint compared to its parent in the tree. And then this way we can also actually describe a human motion if we have a list of these triplets for each joint, for each frame, so that we can show the different rotations, and then this way make our skeleton move and do a certain motion, such as the motion here on the slide, which shows some frames from a skeleton doing a Macarena dance. All right. So now let's talk about a common problem in the context of these 3D motions. Also, again, this problem is also tackled by the first speaker in a different way, but we're going to look at a more distance-based approach. So the problem is called motion retargeting, and it asks the question whether we can impose the same movement of an original skeleton onto a different skeleton with a different morphology. For instance, the skeleton in this picture has less broad shoulders, so shorter shoulders. The old classical approaches are based on simply copying these Euler angles that we talked about in the previous slide onto the new skeleton. This creates all sorts of undesired collisions, like in these pictures, where now the hands are suddenly touching above the head or touching behind the hips, which is something we want to avoid. Especially since this is in our rendered skeletons, we don't render the skull. So in our example right here, the skeleton with shorter shoulders would be penetrating his own skull with his hands, which is of course something that we want to avoid. So how can we avoid such problems? So we can look at it from a different point of view, because we can also represent these human motions by distances. And then when we talk about these distances, we talk about either the bone lengths, like in the left picture, or relative movements between joints. So these are distances between joints at the same frame or at different frames. So and then if when we want to try to retarget a motion, we would like to copy these distances from an original skeleton to the new skeleton, so that we make sure that we keep distances between joints the same, so that we can avoid undesired collisions or retain contacts when we do want them to be contacts. But of course, once these skeletons have an adaptive morphology, we should also make sure that we transform this distance matrix of the original skeleton somehow, so that we have these distances in the same terms. And this can be done by a normalization and denormalization process using the shortest path between two joints. So like in the picture, we have joints U and V, which are the hands of both of the skeleton. And then we want to first normalize this distance by looking at the shortest path in the skeleton between these two joints. Then we find the weight of this path, so the sum of all the length of the bones along this path. And we divide the distance between the two joints by this weight of the path, tau. And afterwards, when we want to denormalize this for the target morphology, we again find the same tau, but for the new morphology, and then use that to multiply this distance, so we have now an adapted distance between joints. And this way we can obtain for all the joints this target distance matrix that we would like to approximate as much as possible, so that we can copy the motion in the best way. So this leads us to a new variation of the distance geometry problem, one that we will solve to solve the motion retargeting problem. So now we removed this temporal component, and now we have a graph G with the vertices V, which represents the set of joints of the skeleton, and then a set of edges E, which represents this target distance matrix that we computed like on the previous slide, so using the shortest paths for the new morphology. And then again, we have this mapping D, which maps a priority to every distance value that we have. But an important difference to realize in this variation is that we have an initial realization of our skeleton, which we refer to as X0 here on the slide. In the practical results, this is the previous frame of the results. So now we're going to solve this dynamical distance problem. Instead of solving it in one go, we're going to solve a series of statical distance geometry problems, one for each frame, and use the result of the previous frame to give an initial realization that we can start off from to help us find this next realization. And again, we're going to find the next one by optimizing the boundary function. So now let's talk about this process that I mentioned before, that we do frame by frame. So at every frame I, we first obtain the target distance matrix at this frame, like shown in the other slide, using the shortest paths. Then we initialize this initial realization using the results of the previous frame. And note that we're all doing this still in the Euler angle space. So we're optimizing Euler angles, and we also end up with Euler angles again at the end of the process. We can have the motion in the same terms that we started out with. And finally, we use a gradient descent to optimize these angles at every frame, so that we make sure that these distances between joints are as close as possible to the target distance matrix that we obtained in the first step. So like I mentioned before, essentially, we're solving a static DGP instance at every frame, rather than solving a single dynamical DGP instance across all frames. And then another important thing is how we choose our priorities. Since joints are important when they're close to each other because we're trying to avoid collision, there's two ways we assign a priority. One way we look at certain frames ahead, which the number like n frames ahead, where n should relate to the frame rate of the motion. And then we check if two distances are going to be close together at some point. And if so, we will assign a higher priority to this distance. Another interesting way that we assign priorities is by using the interaction distance. This is a special kind of distance that tries to predict when two points are moving closer to each other. So this is a distance between frames. You always need 2 frames to compute this distance. So like in this picture below, this interaction distance gets smaller the closer the hand gets to the shoulder. And then we also use this interaction distance. We compute it, and if it's below a certain threshold, then we assign a high priority for the two joints that are involved in this distance. All right. So we developed a Java program that takes two BVH files, which are two files that, like, a BVH file is a file that describes a human motion in a way I described before, so with a list of order angles. And this program takes two of such files as input, one file for the original motion, and then one file that simply describes the adapted skeleton, but not the motion. And then it performs this motion retargeting and outputs the resulting motion as another BVH file. So we did some tests using motions from the motion capture database from the Carnegie Mellon University. You can find on the link in the website. Should you be interested in looking at more motions. I will now show a video clip with some resulting animations. So first we will look at the Macarena motion. So on the left, we will show the original animation. In the middle, we show what happens when you simply copy the angle. And on the right, we show our solution. And the two skeletons on the right have adapted morphology because they have shorter shoulders. As you can see highlighted in red, they are 30% shorter than the original skeleton. All right, let's look at the animation. All right, so here the video is paused. Here we have this picture from the slides that we saw before. You see that in the original, the skeleton now puts his hands above his head, and there's a little bit of space left for his skull. When you simply copy the angles, this space is gone. But in our solution, we managed to retain some space between his hands. All right. Here again, we pause the video to see a similar thing. In the original, there's a little bit of space between the hands on his hips, and that when we simply copy the angles, this space is gone. But when we look at our distance problem, we retain this space. All right, now let's look at a second motion that shows a skeleton that is cold and it's warming his hands to try to keep himself warm. Again, we have the same setup with the original on the left, the two adapted skeletons on the right, middle with simply having angles copied, and the one on the right showing our solution. In this case, the shoulders are made 30% broader. All right, let's see. All right, so here the skeleton rubs his hands together to warm them up. However, since the shoulders are a bit broader, when you simply copy the angles, the skeleton ends up only rubbing his fingertips together. But when we use our targeting method, the hands are actually kept in the same position together. All right, now we will look at the final motion in which a skeleton goes into a defensive pose. Here, I made some slightly more changes to the skeleton to show that the more we change the skeleton, the more our approach starts to suffer a little bit, because it introduces some small extra movements that were not there in the original motion. So now I both made the shoulders and the spine a bit shorter. So now there's some extra movement, for instance, that was not there. So I still want to highlight that we still are capable at keeping this distance between the hands in this case, which was in the original motion, but not when you copy the angles. Sorry. All right. That's the end of the video. Now let's talk about some challenges and some possible future work. When doing some experiments, one motion was quite difficult in particular for us to solve, in which a skeleton sits with his hands under his legs. And then if you make his spine a bit longer, you get, when you copy angles, he puts his hands above his legs. But when we use our retargeting method, he still keeps his hands above his legs because we only look at the relative distance between joints. And then these distances are satisfied, even though the order of the bones might not be exactly the way we want it to be. Also, we did some small analysis that of the motion capture database, which includes several hundred motions, in which we computed two angles, the torsion and vector angle of a joint. And we try to find out possible combinations of these two angles. And we are interested in this because we would like to add some constraints to our algorithm to make sure that we never end up in any unnatural positions. Here on the right in the slide, we have a heat map of the right arm joint, which shows the possible angles it gets into all these captured motions. You see there's a lot of white space, so we could use this to improve our animations even further and try to avoid weird rotations of joints. All right. This was the end of my presentation. Thank you for listening. If you have any questions, you can ask them now.
Thank you very much, Simon. So are there any questions from the audience?
Yeah, if I could.
Please.
Okay, thank you, Simon, for your presentation. Just to make clear the problem, you have originally an animation, right? Then for each frame, you compute the distance matrix between the elements of this skeleton, right?
Yes.
And then you have to detect, you have to adapt the angles. With the angles, you obtain a specific distance matrix and you compute this, the similarity with the target one, right?
Yes, exactly. Yes.
Okay, okay. My first question is, are you using the complete data matrix at every frame? Because you can detect just the angles involved in the changes. You don't need a complete matrix, right? Because it's supposed that that between one frame and the next one, the changes are small.
Yes, this is true.
In this example of the Macarena, right? The legs are not moving. So you can not work with the angles involved in the legs.
Yes, this is true.
Have a reduced problem.
Yes, we kind of do this because we have these different priority levels, and some are very close to zero. So in these cases, if the legs don't move, they're very close to zero. And also, I don't mention this in the slides, but we kind of solve two objective functions. One that measures this difference from this target matrix that you mentioned, and another one that looks at the movement in the original skeleton and tries not to deviate too much from this.
Yeah.
So that we don't make unnecessary movements that were not there in the original.
Okay. And another question is, you may have many solutions with the same value for the objective function, right? Because, for example, you can compensate the distance in the hands with some movement in the legs, putting the
Oh, yeah.
foot closer or something like that, right?
Yeah, I know. Yeah, okay, I understand. Yeah. Okay.
So do you have any idea on how your solving algorithm is working to compensate the difference between your matrix and the target matrix? If they are just moving all the angles just a bit, or just a few angles with very strong movements?
It tries to move every angle a little bit, and then measure the change of the objective function by computing this gradient matrix in a gradient descent. Yeah, I'm not sure if that's what you mean, but
yeah, I mean, because you have to take the difference between two distance matrices, right?
yeah.
So you can have a close to zero value, just moving a bit several points in the matrix, or just a few of them. So what's going on in your algorithm, how it's working? Because you may have many solutions for this problem.
Yeah,
do you have any idea on how the matrices are changing between every frame to detect where the magnitude of the changes?
I'm not sure if I understand the question completely.
Yeah, okay. Simon, if you allow me, I can answer to the question. So yeah, as Simon mentioned, it didn't say explicit in his presentation, but actually we are using for retargeting every frame, we are using this normalized matrix with the distances that are adapted to the new morphology of the skeleton, and also the distances from every join at the current frame to the same join in the same joint at the previous frame. So in practice, to answer to your question, how do I deal with multiple solutions? Because as you mentioned, I could have, for example, a hand that is approaching a knee, or a knee that is approaching a hand. But in terms of distances, this is the same.
Yeah.
So in practice, we try to distinguish between these two solutions by taking consideration the quantity of movement that is already in the original animation. So considering the original animation, we have a strong change in the coordinates of the hand. So we try to reproduce the same also in the retargeted motion. So in this case, it's the hand that will approach the knee, and not the knee that will approach the hand. And moreover, to complete, okay, maybe probably all this is not enough. Now Simon is making several experiments with all the motions that he can find on this big database. And one of the things that we are planning to do, he mentioned to this in the future works, we plan to include constraints in our optimization problem in order to avoid the skeleton to have unnatural postures, because you can imagine some of the solutions that we could get just by looking at the distances are postures, represent more postures for the character that are not natural. So all these solutions that are not good for us, in practice, we plan to take them away by including these constraints that in some cases can be obtained just by looking at the structure of the skeleton. For example, I make always the example of an elbow here that would have the wrong angle. The angle of the elbow is this one. We cannot go on the other side. So this you can derive immediately. But by analyzing the database, we can find. Simon started to find what you see on the screen now. It's one example. Start to find some nice relationships between the angles that can be used for representing the movements. And so if we take them off, we filter off all these postures that are not natural, and hopefully we can converge faster, more efficiently to the right postures.